The next type of circular motion problem we're going to talk about is banked curves. So basically cars going in a circle in an embankment. For example, if you've ever seen NASCAR, especially the Daytona 500, when they're making those the oval racetrack, when they turn on that curve, it's banked. So it has an angle with the ground. So let's say this is our banked curve. Here's our horizontal. Okay, and let's say the banked curve in this problem is going to be 15 degrees. So a curve has a radius of 50 meters and a banked angle of 15 degrees. So this is our road, and it goes in a circle. I'm not going to complete the circle because I didn't draw my picture big enough. But basically this radius of the circle is 50 meters. And here's our car. Let's say it's going this way, on the banked curve. So he's making the curve. It's banked at 15 degrees above the horizontal. What is the ideal or critical speed, the speed for which no friction is required between the car's tires and the surface for a car on this particular curve? So we're doing the first example, which is no friction. So this is an ideal scenario. So if this car were on ice, for example, and this was just a circular track and it was embanked all the way around at 15 degrees, then the car, without turning its steering wheel, it could stay on this curve and stay on it forever. Okay, without sliding. So first thing we want to do is draw a free body diagram. So I'm going to redraw my embankment one more time so you guys can see it. So there's my car. We have mass times gravity pulling the car down. We have the normal force perpendicular to the surface. And we have, that's it. So this is the ideal case, no friction. So unlike the inclined planes, we always changed the mg factor and made x and y components from the weight factor. But this time we're gonna take our normal force. The reason why is because we know that when things travel in a circle, it's because there is some sort of centripetal force pulling toward the center of the circle. Well, this is our center of our circle. It's this way. And you gotta kind of picture this 3D. So our centripetal force is always pointed towards the center of the circle. In this case, it's going to be the x component of the normal force. This one, that's what's pulling it to the right. So you're gonna have to picture this 3D. Okay, so that must mean that this is also theta. Okay, it's the same concept. The reason why this is theta, go ahead and draw out yourself the xy axis and draw yourself a new xy axis with x prime and y prime. Use geometry, prove to yourself that this is the angle we're talking about, not this one over here. Okay, so this one is f in sine, this is f in x, and this is f in y. Our f in x is f in sine theta, and our f in y is f in cosine theta. So we need to write our force equations now. So let's start with our x equation. Some of the forces in the x direction. The only one in the x direction is f in x. The car is accelerating in the x direction. That's the centripetal acceleration. That's what keeps it going in a circle. Okay, let's go ahead and start our y equation. Some of the forces in the y. Well, we have two now. We have f in y going up, and we have weight going down. The car isn't accelerating in the y direction, so this is going to equal 0. Okay, so that must mean f in, well, our y was cosine theta, equals mg. F in x is equal to f in sine theta, which equals m, and acceleration centripetal once again is v squared over r. We are looking for this velocity right here. So we don't know the normal force in this case. So we're going to want to go ahead and isolate for Fn over here in the y equation. Let's divide by cosine theta on both sides. You get Fn equals mg over cosine theta. We want to get rid of that Fn right there. So now we're going to plug this normal force in for this one. They're the same value. You get mg over cos theta times sine theta, which equals mv squared over r. Well, we know that sine theta over cosine theta, that's just tangent theta. Okay, I think this is the equation that we need. We are given the radius, it's 50 meters. We're given the angle, 15 degrees. And we don't need the mass because masses cancel on both sides. So I guess we could simplify it one more time. G tan theta equals v squared over r. Let's multiply r on both sides. You get v by itself. Let's go ahead and take the square root of it at the same time. V is equal to the square root of rg tan theta. There's our equation that we need. Remember to always solve variables first and then plug in your values. Square root of 50 meters times 9.8 meters per second squared times tan of 15. You get, let's see, make sure you're in degrees. You get the square root of 131 point something, and that is 11.4 meters per second. Okay, great. Let's go ahead and do one more problem. This time we're going to talk about friction is going to be required. So a 540 kilogram car is merging onto the interstate on a banked curve. So this is as if you're going to get on Highway 99 or I-5, and you're getting on an on-ramp that is turning on a circle. So once again, we're in an embankment. So here's our car. But this time, we're going to ask what is required frictional force to keep the car from sliding. So this isn't an ideal scenario. This is an actual road. We need to know what is that force that we're going to need to be able to keep the car from sliding in its path. So once again, let's create our free body diagram. We have mg down. We have our force of friction pulling down this way. Because if our car was going to slide, it's going to slide that way. So if force of friction is prohibiting it from moving that way, that must mean it's directed down and to the right. Our normal force is always perpendicular to the surface. Okay. Now let's actually go ahead and draw our xy axis and figure out what is happening here, which thetas are thetas. So we know that we're going to want to use up and down forces. So if this is our Fn and this is our friction, this is going to be Fny. This one's going to be Fnx. Same thing for friction. We're going to have friction F of friction x, and a portion of it's pulling down, F of friction y. We want to figure out where is our theta in both these triangles. This is the point at which I'm going to prove to you where it exists. So if this is our normal xy plane, and we actually went ahead and shifted our plane up theta, so I'm going to take my x-axis and shift it up theta. So there's our theta. There's our little embankment. So this is our new x. We're going to call it x prime. So since we shifted that theta, we also have to shift our y theta. Okay, so this kind of shows where our thetas come from. So this is our perpendicular new y prime. Here's our y prime. So this must be theta. And if this is theta, opposite interior angles are equivalent, so that's theta, which means There's theta. Okay, if that was kind of confusing for you, go ahead and walk through it one more time. Stop the video and do it one more time and make sure you understand where it comes from, because this is probably the most confusing part, where the theta is. Okay, so now we need to go ahead and write our equations. So we have some of the forces in the y direction and some of the forces in the x direction. Let's do y first this time. Doesn't really matter. So we have an up force, normal force in the y direction. That's going to be Fn cosine theta. And then we have two forces in the x direction pulling downward. We have the frictional force in the y direction and mg. So minus F of friction, this time it's sine because it's opposite of the angle. And since our car is not accelerating in the y direction, that's going to equal 0. Let's go ahead and plug in our givens. Fn cosine, and our angle in this case was 7.1, minus F of friction sine 7.1, minus 540 times 9.8, that was our mass, equals 0. Okay, we can go to multiply 540 times 9.8, you get 5,290. So you're left with Fn cosine 7.1 minus force of friction sine 7.1. Okay, that's going to be a key equation. So we don't know the normal force and we don't know the force of friction. Let's go ahead and talk about our x equation. Some of the forces in the x direction are Fn sine theta, because we have it pulling to the right. That's our Fnx. It's pulling to the right, so it's positive. And we also have force of friction pulling to the right. So we have plus the force of friction, and it's the x direction, so it's cosine in this case, equals, and this is what's keeping our car going in the curve, so it does have a centripetal acceleration, mv squared over r. I went ahead and plugged the v squared over r in directly for AC. So we're left with Fn sine 7.1 plus force of friction cosine 7.1 is equal to, let's go ahead and plug our numbers in, 540 times 23, and that's squared. That was our speed, 23 meters per second. And our radius on the curve is 210, so divided by 210. This number is equal to 1,360. I'm just rewriting the same equation. So now we're left with two equations and two unknowns, for normal force and friction. Normal force, friction. So you all know how to do this kind of problem from here. I would suggest you go ahead and stop the video and try to solve for normal force and friction on your own first, because it's just math from here, and then check your answer at the end. Okay, so if you're going to solve this problem, we know that we have two equations and two unknowns. So I'm going to take my first equation up here and solve for normal force. I'm just picking, it doesn't really matter. So Fn cosine 7.1 minus F of friction sine 7.1 equals 5,290. I'm going to add 5,290 plus force of friction sine 7.1 and divide it by cosine 7.1. I'm going to do this all in one step. You should be okay. Okay, so that's what the normal force is. So now that we know the normal force, we can plug it in right here for a normal force. And we can solve for force of friction. We have one equation with one unknown. So here we go. So now that we know normal force, we're going to plug it in right there. So we get 5,290 plus force of friction sine 7.1, all divided by cos 7.1. So that's normal force. Normal force is being multiplied by sine 7.1 plus force of friction cosine 7.1 equals 1,360. Okay, so now you have one equation, one unknown. Your force of friction is unknown. That's what we care about. So let's go ahead and solve for it, one step at a time. So the first step I'm going to do is I'm going to divide this number, 5,290, divided by cosine 7.1. And I'm also going to multiply it by sine 7.1 while I'm at it. You get 658.9. So I just did this, 5,290 divided by cosine 7.1 times sine 7.1. So we're done with this part. Now we're distributing right now. This is a distributive property. Now we're going to multiply this variable times this one. So f of friction, sine 7.1 times sine 7.1. So basically sine 7.1 squared. Sine 7.1 squared. You get 0.0152. 0.015, and round up, we get 3. Plus, we have another cosine 7.1. Cosine 7.1 is equal to 0.99. So force of friction times 0.99. Maybe we'll go one more digit. Equals 1,360. Okay, I want to put my likes together. So this one is a number, this one's a number. This one has force of friction, this one has force of friction. So I'm going to subtract 658.9 on both sides. And then I'm going to add these two together since they have the same variable, force of friction. So 0.0153 plus 0.992, and we get basically 1.0073 times force of friction, which equals, so let's subtract these two, 1,360 minus 658.9. Now if we divide over, let's just say it's basically 1. You get force of friction is equal to 696. We can go ahead and say 700 newtons. Because if you used 1 instead of 1.0073, you would get 701. So let's round it, 700. Great, now you should be able to do homework 3.